All right, let's dive right into this explainer. Today, we're unpacking the invisible physical forces that literally power our modern world. We're talking about the hidden energy making the exact device you're watching this on work, all the way up to the massive industrial machines that keep our cities humming. And it really all comes down to the absolute magic of electromagnetism.
But before we get into the heavy physics of it all, think about this relatable, everyday mystery. Have you ever noticed your lights briefly dimming when you turn on a heavy appliance, like a vacuum cleaner or maybe a washing machine? Stick with me here, because the physics we're about to explore holds the exact secretive answer to this very common phenomenon.
So here's our roadmap for today. First up, we'll demystify electromotive force. Second, Faraday's law of induction. Third, we'll look at generators, motors, and back EMF. And finally, we'll see exactly how transformers safely route this immense power right into our homes. Let's get started.
Section 1. Understanding electromotive force.
Right out of the gate, we've got to acknowledge that the term electromotive force, or EMF for short, is actually famously misleading. To understand why, let's look at the difference between EMF and voltage using a really simple water analogy. Think of EMF as the pump. It measures the total energy supplied by a source, like a battery or a generator, to each unit of charge. It's doing the raw mechanical work to move the water. Voltage, on the other hand, is the resulting pressure difference between 2 points in the pipe. So the pump does the heavy lifting, and that resulting pressure difference pushes the flow. There's no physical pushing actually happening. It is all about energy transfer.
Just to be crystal clear, EMF is absolutely not a physical force. If you're looking for a simple electrostatic push or pull, you really won't find it here. Even though Alessandro Volta coined the phrase electromotive force way back in 1800 when he built the very first battery, modern physics tells us it simply represents the work done per unit charge. It's an energy conversion metric, not some kind of tractor beam.
Section 2. Faraday's law of induction.
Let's rewind a bit to trace the timeline of this whole revolution. In 1800, Volta gives us the battery, which is chemical electricity. But the truly world-shattering breakthrough comes in 1831. That's when Michael Faraday discovers that by varying a magnetic field over time, you can actually generate an electric field pretty much out of thin air. Now, Joseph Henry observed this independently in 1832, but Faraday published first. This 1831 discovery was a massive turning point for humanity, honestly, because it meant we could suddenly generate electricity simply through motion. Picture Faraday's classic experimental setup. He initially found that simply placing a static magnet near a closed circuit does absolutely nothing. If you have a stationary bar magnet sitting right next to a wire loop, the meter is going to register zero current. A dead, static magnetic field has no effect whatsoever. But here is the brilliant breakthrough. The very moment that magnet is actively pushed into the loop, creating relative motion, the meter suddenly deflects. By moving the magnet, you're changing the amount of magnetic field, what we call the magnetic flux, passing through that loop. And that changing flux induces an electromotive force, which drives a brand new electric current. And it gets better. If you pull the magnet away, reversing the direction of the movement, the meter instantly deflects in the complete opposite direction. It's the continuous dynamic change in the magnetic field that's doing the work and generating the current. Literally, if you stop moving, the power stops.
This brings us to two core rules of the universe. Faraday's law tells us that a changing magnetic flux induces an EMF. But then Lenz's law adds this crucial, almost rebellious caveat. The induced current will always flow in a direction that produces its own magnetic field to oppose the original change. Why? Well, it's because of the fundamental conservation of energy. If it actually helped to change, you'd get infinite free energy, and we know that's impossible. So Faraday dictates the creation of the EMF, and Lenz dictates its stubborn, opposing direction.
Section 3. Generators, motors, and back EMF.
Okay, let's take these abstract laws and actually build a machine. Imagine a simple wire loop suspended between the north and south poles of a magnet. If you physically apply force to spin that loop through those invisible magnetic lines, the magnetic flux passing through the loop varies wildly over time. Just like Faraday's moving magnet, this physical motion induces an EMF. You have just built the foundational mechanism of a power generator.
And here is a totally mind-blowing fact of engineering. Generators and motors share the exact same fundamental physical construction. They just run in reverse. A generator takes mechanical energy, like a wind turbine spinning that loop, and converts it into electrical energy. But if you pump electrical energy into that loop from a battery instead, the current interacts with the magnetic field to create a physical twisting force, causing the loop to spin. That's a motor.
They are literally two sides of the exact same electromagnetic coin.
But wait, there is a catch. Because a motor is physically spinning a coil inside a magnetic field, it's actually simultaneously acting as a generator while it runs. Thanks to Lenz's law, this newly self-generated EMF acts as a rebel. It actively opposes the input voltage that's powering the motor in the first place. We call this back EMF. It's this invisible opposing voltage generated by the motor's very own rotation.
Okay, so let's bring this all the way back to our vacuum cleaner mystery from the very beginning. When the vacuum motor is off, it's obviously not spinning, so the back EMF is 0. The second you hit that power switch, there's no back EMF yet to resist the house voltage, so the motor just gulps down maximum current. This massive, greedy initial draw causes a temporary voltage drop in your house's wiring, and boom, your lights dim. But as the motor rapidly spins up to full speed, that opposing back EMF grows stronger and stronger, significantly choking off the current drawn from the wall. Once it hits operating speed, the current normalizes, and your lights brighten right back up. Mystery solved.
Section 4. How transformers power homes.
Inside a transformer, power takes this incredibly precise, almost magical journey. First, alternating current enters a primary coil, generating a constantly pulsating magnetic field. Second, a laminated iron core captures and guides that changing magnetic field over to a secondary coil. Now, the iron is laminated, meaning it's built in thin, insulated slices to prevent stray, swirling pockets of electricity called eddy currents from heating up the core and wasting energy. Finally, as that guided magnetic flux hits the secondary coil, an EMF is induced. Power is magnetically transferred completely across empty space with literally no physical wires connecting the two sides.
Now, why go through all this trouble? Well, because 220 volts, or 110 in some regions, is the safe standard for homes. But out on the highway, power transmission lines carry hundreds of thousands of volts to push electricity over long distances without losing power. If that massive city-level voltage hits your microwave, the device would instantly explode. So transformers are the crucial gatekeepers that step that massive voltage down to a safe, usable drip for our houses.
And honestly, the most beautiful part of transformer design is just how wonderfully simple the math is. To change the voltage, you just alter the ratio of wire turns between the two coils. If the secondary coil has more loops of wire than the primary, it acts as a step-up transformer, amplifying the voltage. If it has fewer turns, it's a step-down transformer, decreasing the voltage for your house. It's an incredibly elegant, infinitely scalable application of Faraday's law.
There is one strict, absolutely non-negotiable rule here, though. Transformers require alternating current, or AC. If you used direct current, DC, you generate a fixed, frozen magnetic field in the core. And remembering Faraday's law, without a changing magnetic flux, there is zero induced EMF. Absolutely nothing happens. The continuous pulsing change of AC power is the literal heartbeat that makes transformers, and frankly our entire modern grid, possible. Which brings us to the end of our explainer. Every single time you flip a light switch, you're commanding invisible magnetic fields that are continuously shifting, interacting, and inducing energy across miles of wire, just to power the screen you're looking at right now. It really makes you wonder, as you go about your day today, what other unseen physical forces are quietly shaping the world around you at this very second? Keep questioning, keep learning, and I'll catch you in the next explainer.